I've never used one of them, so I don't know.
Oh, I don't know.
How long will 19% last you?
I don't know.
It says in the corner when you click on it. It says 19%, 2 hours and some odd minutes. So normally it does. Normally when you click on it down there,
No, you gotta hover.
there you go. So. All right, ladies and gentlemen.
Mr. Brandon, did she get her apple that she wanted?
I don't know. Why are you asking me? Thanks a lot, Victoria.
I totally forgot.
You're helpful. Not.
No, I'm very, very, very helpful. Wait, can I have my dollar or apple?
You can have your dollar. You can have your apple.
Can I have a dollar?
No, because it's not your dollar. You can have your dollar.
We agreed, a dollar or an apple. I prefer the dollar.
You know, here's the thing. Just because you say it doesn't mean we agreed on it. That's the part you're missing. What? 2 tests? 2? You got to do 2 tests? Oh, okay. Yeah. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 14. Perfect. All right, ladies and gentlemen. So, who do you want to do something with, and what do you want to do? Do you want to do something publicly with them, or do you want to have just a private dinner alone with them? Who wants to go first? All right, Kiana, go ahead.
Private dinner.
With?
I don't know. Let me just go with my last name. Marilyn Monroe.
Okay. All right. Fair enough. Again, I didn't ask who it would be with, but if you know who it would be with, that would be great too. Ethan?
I would play a game with Dirk Nowitzki.
Same team or opposite?
Opposite.
Ooh, man, nothing like being schooled by your idol. But okay. All right. Who else? Wait, change the line. What?
Because
Let's make this quick, though. Come on, this is not an all-day event.
I can hit his own move against him.
Right. Not if he's defending you. You can't. Anyway, moving on. Next. Okay, go ahead, Kevin. What?
I would like to perform live with my favorite band. It's called Foo Fighters.
Okay.
Yeah. Just perform live.
Okay. That'd be cool. All right, Alex, what do you got?
I'd rather eat dinner privately with Drake.
Okay. Good thing I asked yesterday's question, because now you guys all got a person in mind who you would be doing things with. Go ahead, Faith.
Dinner with Robert Downey Jr.
Not Brentley Gilbert?
I did one yesterday with him.
Oh, she's spreading the wealth. Okay, very good. All right, Jennifer, do you want to have a private dinner with somebody, or you want to perform publicly with them? Okay, do you know who it would be? No, but if you had the choice, that's what you would go with? Right? Okay, that's fair enough. Ethan? Dinner? You know who with?
Scarlett Johansson.
Oh, good choice. All right. Lucy?
I don't know who.
Okay, would you rather do something publicly where everybody could see it?
Yeah.
Okay, fair enough. Jimena? You know who with? Okay.
Okay, are they paying for the dinner?
Don't worry about how the dinner gets paid for. It's free. You're with somebody who, when they walk in the restaurant, they're like, don't worry, it's free. It's on us. So which one, Victoria? Now that you had to put a qualifier on it. So, well, I want to go to McDonald's with the person.
Yeah, for real.
What if McDonald's is their favorite meal?
No. Probably publicly then, because I ain't trying to eat from McDonald's. Same person I did.
I don't remember who that was. Can you tell me again, or don't you want to? Okay. All right. Helen, what are you thinking? Dinner with? Not sure. All right. Jaslyn? With?
I'll go with Zach Bryan.
Zach Brown?
Zach Bryan.
Brian, sorry. Okay. 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 All right, Mariana. Private dinner with? You don't know? Just by yourself? No, I'm kidding. You're okay, right? Okay. All right. All right. All right. Faith changed her mind.
No.
She now wants somebody other than Robert Downey Jr.
No. Well, I would do Jim. Never mind.
Who?
Anyway, my computer's not. It's like, it's not loading.
Okay, then you gotta wait the 10 minutes and head down to the library because either that or restart it. The library. That room down at the end of the hall down there, a lot of books, things like that. The library. Yeah. Yeah, the library. Okay. Okay.
It's a library.
I'm thinking. Christopher or Christian?
Christopher.
Oh! We should start a pool, ladies and gentlemen. Every day, everybody throw in a quarter and pick somebody who's late, and the winner gets all the money.
Or an apple, which is face it.
Faye's the only one who wants an apple.
Yeah.
Nobody else does. What?
I want a green one, please. A green one, please.
You want green peas? Oh, well, no, not all peas are green. There are yellow ones, too. Anyway, all right. No. Leave your desk where it was. You don't need to slide it over there. There's plenty of... Back. Toward Helen. Good, perfect. Sit down. I get to rearrange the seats in the room, not
Why
you.
are they like this?
Why not?
It's weird.
This is the way it was when we first started out the trimester. Ew. How quickly you
complained
forget.
about how they were the first day.
You complain about everything.
Yeah.
Christopher, put away the food. You can't eat in here. Okay? You can't eat in here, sir. It's a science room. That's unhealthy for you. Especially when you get chemicals on them and then you die from it. Bad for your health. Bad for your health. All right. So, Miss Stark, you going to go to dinner or are you going to perform publicly?
Dinner, but I don't know who with.
Okay.
What about you, Mr.?
I would do something public, but I would go golfing with them. I don't care who it is.
Tiger Woods.
Of course.
No, not Tiger Woods. If it was yesterday, it would still be Michael Jordan, and we would golf at his golf course because his golf course, they have drone service where they will put drinks or food on a drone and fly it out to you, whatever hole you're on, and drop it off for you.
That's kind of cool.
I think that would be cool.
At your exact spot.
What?
At the exact spot that you are.
Yeah,
Awful.
because all the carts have GPS trackers on them. So they know exactly where it's at. You send it, and it goes right there, and it drops off what you need.
It's kind of sick.
Well, hey, you know what? There's good uses for technology sometimes.
Yeah, I believe it.
Yeah.
You're a golfer.
I love to golf, yes. I'm not a good golfer, but I love to golf. All right, ladies and gentlemen.
Golfing is fun.
Today we've got to get some stuff done. Yesterday we started on the Boyle's Law Lab. We want to give you some time to finish that up. Then we're going to actually talk about Boyle's Law today too. So the first thing we need to do, ladies and gentlemen, is go into Google Classroom and open up Boyle's Law Lab and the data table, please, just to make sure that we have everything that we need. All right.
I fixed it. I'm good.
You're good?
Yeah.
Did you shut it off
Yeah, I did.
and turn it back on?
I did.
That normally works 9 times out of 10. I could now charge you a $75 fee for servicing your computer,
No.
but I won't do it. It's
I
okay.
serviced my own computer.
No, I gave you the idea.
He told you what to do.
Okay.
I mean, no, you didn't.
Okay. So up at the top, ladies and gentlemen, your pressure should be into here so that you got those 2 points done. Yesterday we left off. You should have added your graph to here, ladies and gentlemen. Okay, you should have added your graph to here. So Jennifer, you weren't here yesterday. I put an alternate assignment in there for you. You can work on that and then get it into me. And if you have questions, let me know. There's an interactive where you can go to collect your information, and then you can put it in there, and then you can make your graphs. Okay? So remember, ladies and gentlemen, the graphs came from page not found. Okay, let's do this then, ladies and gentlemen. All right. Classwork. Boyle's Law. Okay. All right. So you put your numbers in here. By the way, one important thing yesterday, ladies and gentlemen. If you did not take out this point at 20 milliliters, please do so, because we were sure that that point was not good because the numbers did not go down far enough like they should have. Now, your numbers in here would be different than mine. Don't worry about that. These are just some numbers I put in there to be able to show you your graphs and things. Your graph, ladies and gentlemen, okay? Please make sure you've changed the X and Y axis. Please make sure that you have a title on it, and then you can copy it and paste it into the lab. So you can hit the copy chart button up here and paste it into your Boyle's Law lab like I did here. Then, ladies and gentlemen, there is a second graph on here. That graph gives us a straight line because we switched. We did a little mathematical trick to this. Instead of using pressure, we took the inverse of pressure. When we did that, ladies and gentlemen, our line came out very straight, which is good because that's the way it should come out. And now we have volume versus inverse pressure, but we get a straight line from it. And again, the advantage of this straight line, ladies and gentlemen, is I could find a point somewhere over here, somewhere off of the graph if I wanted to. Okay? Because what we have is we have a constant relationship, a straight line from it. We talked about that yesterday, ladies and gentlemen. So then this should go into your lab on the second page here, ladies and gentlemen. Right down in here, that is where this graph would go, ladies and gentlemen. That should be done. Now, please keep in mind, check your graph. Do you have a title that doesn't say title? Do you have a label on the x-axis and on the y-axis telling us what you measured? Do you have units on both of those axes? So volume, what unit was it? Pressure, what unit was it? Inverse of pressure, what unit was it? That's how you get your 4 points for the graphs. That's 8 easy points that you can get. Okay? Now, down here, ladies and gentlemen, are questions. Okay? So, what type of relationship, inverse or direct, constant versus non-constant, is shown in each of the two graphs? So graph number 1 was pressure versus volume. Graph number 2 was volume versus inverse pressure. So when you look at those two graphs, ladies and gentlemen, tell me, are the relationships inverse or direct? Are they constant or non-constant? Nope, Alexis, somewhere in the first 3. Nobody needs to sit in the back. We don't need those seats back there. Okay? All right. So what are they? Basically, look at the graphs, fill that out. Okay? Now, for question number 2 here, ladies and gentlemen, again, I want you to take your pressures from the table up above and put them into here. You can literally copy and paste them. Let's take out this row down at the bottom, ladies and gentlemen. Just take out this 20. Why? Because we know it wasn't a good point anyway. So you don't have to delete the row, just take out the point. Put in your pressures, ladies and gentlemen. And then come up, grab a calculator. And you are going to take your volume times your pressure and get an answer here. So we'll give you a few minutes to get this calculated. Should have number 1 and should have number 2 done in a few minutes. Yes, Christopher, what can I do for you?
Did you get the pressure from the top table? That we did?
The pressure from the table up in this lab.
Yeah,
Yes, those pressures you bring down here. Not the inverse ones, the ones that you copied into up at the top under the procedure and observations. So let's go, ladies and gentlemen, get this done. If you have questions about anything, the graph, the data table, anything like that, now would be the time to ask while you're working on things so I can correct this for you.
Because you can so you collect your data, you know, and I was like, what do you use the power lift? Let me see. Yeah, he works or he told me he was like a coach for like the college of that's why he and you can watch the video.
Maybe you can't do it. Stupid.
I know, but it's really in the long haul it's gonna be cheaper than the
But yeah, obviously. They tend to make this stupid.
So what we did is we actually measured the pressure in the so it hit that because then they no, because like so here under 1,000 we got spent. That's what I'm saying. And now we'll go down to you guys stop. I know this
All the
and then all the
things.
they also have I asked it's early. It should look like this.
Yeah, I feel like I don't know why they're.
And then no, and then no, this is the whole angle that used to work. Here's what I was thinking. That's what no, see. Alec, he's like, you gonna join the late shit up.
Oh, should I join? Bro, I feel bad for
So now you're bro, look, no, you don't change. I'll pick you up. But somewhere here, 870%. And after school, we could get your. I'll get the numbers. Now, you go into the. That's true. I was thinking about that.
Yes, you just multiply them.
Oh, bro, I don't know. In that one, the whole like numbers. It's such a nice like computerized. Like no, except this would do it.
Okay, I'll talk about that in just a second. Just for now, you have those. Make sure you have that.
He went to Excel. Oh my God, you can do this. Right? He gives me a head nod.
Make sure you're good with
No,
your own.
he just like gives me no, and then he walks away.
Okay. If you get done, ladies and gentlemen, we're giving everybody a little bit of time to get done. So just wait. We'll talk about the next question in a minute. Okay. But give everybody kind of a chance to get caught up. Okay. And again, if you have questions, please call me over. I will be happy to help you.
I mean, she was dating him though, but he looked like Mr. Irrelevant. No, I'm so serious.
Sure, Kevin.
Dude, their slide is nice.
Okay.
I was like, yo, I don't know. These are cool. I'm like $100, and then he showed me everything. I'm like, all right, now I'm coming.
I didn't say no to this again. I should.
Gentlemen, you good?
Yeah.
Yeah, I'm good.
You're not done.
I mean,
He's meeting with everybody.
Right. So you're not done, but you're good. Okay. Come on, get it finished.
So cute. Yeah.
I felt strong there. That was me, my dad.
I know, dude. No, I saw you with 225 for 8 and I was like, because there's a guy that looked big and started like 60, but I think he was just aesthetic. Good. Because he was only doing like 165, and then I put him
I'm just confused now where what we put. Is that just in the graph?
On the graph, remember, what does it mean to be direct? In a graph, what does that mean?
It's like 2 on each side.
Bro, you give it, they don't care if you stand or what direction. Bro, we can really get it. There's a whole belt jump in
Down is the correct. Up down is greatest constant. Greatest constant. Up or down? Greater curve.
It's just like aggravated.
Good.
It's close to your head. I figured you would.
I mean, it's right, you're literally right by my house.
Oh, bro, you know it's a 10-minute drive from my kid. Just get on the bridge and go straight.
Okay.
Yeah.
Because it's almost close.
Inverse. Okay.
I'll pitch with you. I'll cut you.
And then the other one is direct,
I'll see my dad.
right?
Because it really, I feel probably in the morning.
And then
I mean, that might be a hassle.
You could,
It's right by my house.
based on your graph, you could go with what you have to go with what your graph shows. Your graph would hopefully have been a little bit straighter, but it's not.
But doing it before school, and then I just had the whole
That's okay. That happens. It's all right.
Mr. Graham.
Yeah.
I figured out
There's no plenty for this is gracious, bro. Last time I
Constant means what?
This one will be constant because it's still going.
No, that's constant.
Right?
Okay. All lines will continue.
Yeah.
These stop because we ran out of points. All lines will continue. The question is, to be constant, you need to be a straight line.
This is a straight.
To be non-constant, you need to be a curved line.
So this one will be the
Well, when you look at your line, if it looks curved to you, yes, non-constant. Look straight, constant.
That one that you're looking at was non-constant.
Literally just be a 50. That's for 25.
The first
Who was that? I'm sorry.
You got the initiation fee covered. So
You need her. Yeah, okay, but do you need her for a long time or should she just need her?
no, I told her it might be next
Okay.
Friday.
Okay, I will let her know. Thank you. Bye.
They should be the same number.
Jennifer.
Yeah, please. Yeah, you can just read through too and I'll fix it. But I'm like, yeah, charge me for today. I'll charge you tomorrow.
Whichever one you want.
Thank you.
You had it just fine. Next Friday.
Press control.
Yes. Faith, it's gonna give you the same thing. Yes, it is. That's what I said.
No, really. First of all, stop. If these numbers are the ones you collected here, right? Those were supposed to go into your. Okay, then for that, they're basically the same numbers, so don't worry about it. Okay, I thought you were telling me they were wages. If they rounded it, they come. We're not gonna argue about 118.9 versus 119. We're not gonna argue about that. That is basically the same number. No, I understand. Now that you explained it, that is a lot easier for me to understand.
That's why I told her it doesn't matter which one she uses.
Correct.
She
All
just
right, anyone need more time with calculating the numbers? Hey, look at me. Anyone need, Alex, I'm up here. Anyone need more? Stop watching the video or whatever you're watching, dude. Then why do you keep staring down at her screen?
He's looking at the calculator.
No, he's not. I can see where his eyes. Okay, again, I don't know why he's looking down at her screen. Are you done?
Yeah.
Done. Everybody done? Yes? Not yet. You had two more to go when we were there.
I know I'm done with the table.
Okay, that's what I meant.
Oh, yeah.
Sorry.
He's asking.
That's what I meant. Thank you. I meant that you're done with the table because now we can move on to the next question. Now, the next question is one that I've asked a few, probably dozen times on different labs. And yet people still screwed up. What I am asking you to do in the next question is compare the answers from the above calculation in the box below. So from this table, the numbers that you just calculated here, I'm asking you to compare them. Now, when I say compare things, all right, Ethan, up here. Brianna, come up here real quick. Hurry up, hurry up, hurry up, hurry up, hurry up, hurry up, hurry up. All right. Okay. Now, how would you compare our heights? That doesn't compare anything. That's what I mean. That's the kind of answers I've been getting. They're medium. How would you compare our heights?
Ethan's taller than all of you.
Okay, so we go from taller to smaller. So they're not the same, right?
No.
Okay. We're going from a smaller to a taller height. Okay. I'm asking. Thank you. Thank you. What I'm asking you to do is look at the numbers. First of all, look and see if they're the same. And I don't mean exactly the same, but I mean very close to each other. Are all the numbers very close? Or is there a difference between them? Then, if you see that there's a difference between them, now what I'm asking you to do is see if there's kind of a pattern. So in other words, as we go down the list, if the numbers are not the same, do they get bigger? Do they get smaller? Or do they get bigger and then smaller? Now, if they get smaller, you could still say that. We could compare them and say, well, we don't get the same number, but the numbers get smaller as the volume goes down. The numbers may get bigger as the volume goes down. Or there is another option, which is there's absolutely no pattern there. The numbers go bigger, and then they go smaller, and then they go bigger. What I'm asking you to do is do more than say they're medium. They're all numbers, okay? I want to know how the numbers compare to each other. I want to know if they're close to each other. I want to know if there's a pattern. I want to know if there's nothing. Yes, sir. So again, if they're not the same, then is there a pattern to them? If there's no pattern, you just put the numbers. There is no pattern to them. They go up and down. It's very hard to compare them, okay? So that's what you're doing in that next box.
For the pressure and volume, like the numbers.
For the last box, you just calculated the numbers with.
Okay.
That's the one. Yes, sir. So we're talking about these numbers here that you just multiplied together and got the answer from. That's what we're talking about. That is what we are talking about. Okay? Thank you.
Dude, I didn't have to pay for my own gas.
Yeah.
You said, what?
You ready to go?
Oh.
I started giving my mom gas.
Okay. I was about to.
Okay, anyone need more time with that second question?
Yes, sir.
Sure.
Or that question, I shouldn't say that second question. Last part.
No, we can do that. Okay. Let's go to the casino. Bet it all on black. If we win, dude, we won't use the house. And if we win, then we win the house.
Take another mortgage out for the house.
That's what my dad did.
By the way, that's a good plan, gentlemen. That's how they build those big hotels and casinos in Vegas, is by people who come in and bet the house.
And Oneida.
Yes. But Oneida is a little more understated.
Where'd you get the? Yeah, I brought it up. Okay, let me see the order. Oh, see what okay.
Do you know me? No. What's your name? Bro, she's in the building. It's open. They wrote already?
How for sure.
I thought it was I don't know, because we're still in the final four, no? March Madness, guys.
By the way, ladies and gentlemen, oftentimes in science, you are asked to look at data and decide what you think about the data. Now, again, some people will look at numbers and go, oh, those are way far apart. And other people will look at numbers and say, well, those are close together. Please remember, when you're looking at numbers, Faith and I got in an argument a minute ago about her numbers being different. Because the one graph took the number 18.95 and made it 19.0. Is 18.9 and 19.0 very different? I would say no, but other people are like, oh my gosh, that's a huge difference of 1/10. You're talking about 1/10 in a number that is in the hundreds place. That is not a lot of difference. And when you round numbers, again, it's okay to round numbers. And Faith, I'm not trying to say you did anything wrong. I'm just saying this is one of those things where some people look at numbers and go, these numbers are far apart. And other people look at them and go, well, they're fairly close together. The numbers that you got when you multiplied together were numbers that were in the thousands, right? Okay. So if you have $4,217 and someone else has $4,210, is that a big difference?
Not really.
$7 out of 4,000? Probably not. Somebody else will look at, hey, that dude's got $7 more than me. That's a big difference. You know, you got to look at things sometimes based on how big the number is. If you're talking about 1.2 and 2.1, that's a big difference. Why? 2.1 is almost double 1.2. That is a big difference. When you're talking about 4,210 versus 4,217, you're talking about less than 0.5% difference. Less than that. That's really not that big a difference. Okay? So again, please understand that. All right, good with number 2 there?
Yeah.
All right, let's move on to number 3. There are 4 variables that affect the gas: pressure, volume, temperature, amount of gas. 2 of those variables we changed in this lab. 2 of the variables we had constant. All I'm asking you to do is tell me what 2 we changed, what 2 we held constant, because you either had to do one or the other. You either had to change it or you had to hold it constant. So in there, these 4 variables, pressure, temperature, volume, and amount of gas, each one goes in one of the 4 boxes. Which one does it go in? Where's your computer? Oh, okay. Sorry, I didn't see that. Thank you.
Yeah.
Thank you. I was like, man, come on. Oh, that's fine. I didn't see that. Slide it over there. Yes, sir, Ethan.
What's the difference between a variable and constant?
Okay, great question. If you didn't know that great question. A variable is something that changes. And a constant is something that stays the same. No. Constant is something that does not change. So we changed 2 things in this lab. 2 other things stayed the same. Okay? By the way, if you can figure out which 2 things changed, the other 2 had to be constant. Boy, Ethan, Unit 1. Definition of a variable, definition of a constant. I understand, but we've been using it ever since.
I know, but I just forgot. That's all.
You also
No. Then you didn't learn it.
you also bring up in math.
Yeah.
I quit.
Where do you get that from? I mean, they're good.
All right. For number 4, ladies and gentlemen, number 4, you should have an easy time answering if it is inverse or direct, because all you need to do is look at the first graph we made or look at the data table for pressure and volume. And in an inverse relationship, the variables go in what direction? Opposites. Opposites. In a direct relationship, they go in the same direction. So they could both increase or both decrease. So I don't care if you look at the graph. On a graph, you should know what an inverse relationship is. The line goes how? Down. Or if you look at the data table and say, okay, what's happening with pressure and volume? And looking at the numbers. As you go down the chart, down the table, is the volume increasing or decreasing? Is pressure increasing or decreasing? So, what we just did was also, hey, please listen. We just answered the second part of this question for you. How do you know? Well, when you look at the numbers in the table, if both sets of numbers are going in the same direction, that is how we know it had to be a direct relationship. If the numbers are going one up, one down, that's how we know it had to be an inverse. Or you could use the graph to say how you knew. When I looked at the line of pressure and volume, it was going this way. That tells us that it is this kind of relationship. So this question, don't just give me inverse or direct. Tell me how you know. So you have to use something from the lab to justify you saying it is inverse or direct.
Oh, bro. I'm about to say Nicole. Sure.
That will read.
Nicole now.
None of them had shown up yet, so she said to come down at 8:15.
Okay.
So I'll see if any of them show. Otherwise, I'll maybe get.
Okay. I'll be here either way.
Are we just doing the boys notes?
Yeah, then we're just going to do the notes, and maybe I get into a little bit of the Charles, too, depending on how far we go. So, we'll see. Okay. Thank you. All right, anyone need more time with question 4? Was that a yes?
Yes.
Okay. Victoria, what do you need to get from Alexa?
So I didn't know how to write it.
But now you're just copying it from her. Don't do that.
Well, I have my own thinking in it too.
Okay, but give me your own thinking. Don't give me hers. Okay? Hand her computer back to her. I don't mind you guys working on things together, but you got to come up with your own stuff. They shouldn't be that bad. I don't know. I can't see. It can't be both. Okay. No, they don't. When you look at the pressure and the volume in this lab, there is only one relationship between the two. Do not use the one that I did the trick with. When you look at pressure and volume and what's happening to the numbers for volume and the numbers for pressure, there is only one relationship. You cannot be inverse and direct. Inverse and direct would mean your line would go up and then come down. That doesn't happen. Okay? That does not happen in this lab. You can either look at the graph, the first graph we did. The line is going one direction. You can go back to the numbers that are in your table. But it is either inverse or direct, ladies and gentlemen. And again, how you can know that is by looking at these numbers right here. These numbers are going down. What is happening to these? They're either going up or they're going down. Since these are going down, if these are going down, that is a what kind of relationship? Direct. They're going in the same direction. If these are going down, which they are, and these are going up, then it is not a direct relationship. Then it is an inverse. That can tell you which one. All right, ladies and gentlemen, that was the final question in the lab. So please take and turn it in now. We'll give you a couple of minutes to finish up, ladies and gentlemen. If you have questions, now is the time to raise your hand and ask. Otherwise, you should be done with the lab and it should be turned in.
Yeah. Yes. You know, like as soon as you're 18. Yep. So you're destroying guys. How old are you? Too easy. I like you're my
When we're done, can we turn it in?
Yes, I would hope you would. I want you to. I want you to turn it in right now. You should be done. Is there anyone who needs help with anything, has questions on anything? All right, ladies and gentlemen, if you would, take and open up your EISN and get to slide number 18, please.
Mr. Grant, when's our next quiz or test?
Your next test is probably next week, Wednesday.
Okay, that will work out perfect. So I'm leaving. I won't be here Friday.
Does he call you out for the whole class?
Okay. So we just did the lab on Boyle's Law, ladies and gentlemen. So let's review what we learned. Boyle's Law says the pressure of a gas will vary inversely proportionally to its volume at a constant temperature. Now, it doesn't say this in here, but it's also a constant what? Pressure, volume, temperature. What are we missing? The amount of gas. The amount of gas is also held constant. In a lot of gas laws, they will not say that because they just assume that people understand that the amount of gas is held constant. So what Boyle's Law means is that P and V are in an inverse relationship. Pressure goes up, volume goes down. Volume goes up, pressure goes down. Now, if you remember, we told you to think about pressure. It is how often a particle hits the walls of its container, correct? How often? So I have a ball that bounces and hits that wall, travels across the room and hits that wall. And it does it once every second. So it hits that wall one, hits that wall one, hits that wall one. Yes, it is. So now, ladies and gentlemen, we are going to take this wall and we are going to move it closer. So now that ball doesn't have as far to travel. It hasn't sped up. It hasn't slowed down. But now, because it only needs to travel half the distance, does it hit the wall more or less often? More often. Now, instead of taking a second to get to that wall, if I move that wall halfway here, it only takes a half a second. So it will hit the wall in a half a second, and in 1 second bounce back and hit the other wall. That's twice every second. That means pressure has gone up. And that's what happens in this relationship. If you move the walls of the container closer, the particles inside will hit them more often. Now, the other opposite can happen as well. I could take this wall and I could push it away. What that means is it's going to take longer for 1 second for it to get to the wall and hit it. So it's going to hit the wall how? Less often. Less often. Maybe it takes a second and a half to get to the wall. Bounces back, hits the other wall a second and a half later. Okay? That is hitting less often. That means that pressure is going to go down. That is what we found in this relationship. You make the container bigger, the pressure goes down, as long as you don't change the temperature or amount of gas. Temperature and amount of gas are held constant, meaning the ball cannot move any faster. That would be temperature. And I don't put any more balls into the container. P times V equals K. Anybody know what K stands for? Nope. 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 What? Nope. It stands for constant. It stands for constant. And you may be going, well, why do they use K and why don't they use C? Nope. C is not, a lowercase c is not Celsius, but you're right, it could be. Just like a lowercase k is not Kelvin, a good guess. But C is used in a very famous formula. E equals mc squared. C actually means the speed of light. So they didn't want to use C as a constant here because that's already being used for something. Okay? It already represents a number. Okay? So we use K here. So what this means is if you know a pressure and a volume, you can calculate a constant. A constant is a number that doesn't what? Change. That's what a constant is. And as long as we don't change the temperature and as long as we don't change the amount of gas, this constant will hold. So what that means is somebody figured out, well, if P times V equals a constant, a new P times a different V would have to equal the same constant. Otherwise, it's not a constant. And if this equals K and this equals K, they should be equal to each other. And this would allow us, ladies and gentlemen, to find the volume of a gas or the pressure of a gas at a volume we don't know. Okay? So do you remember in the lab yesterday? We're going to do a real quick calculation here just to show you this, ladies and gentlemen. Just to show you this. In my lab yesterday, ladies and gentlemen, at a pressure or at a volume of 25 milliliters, I had a pressure of about 231 kPa. And that was as high as my sensor would go, correct? Would someone with a calculator please take 231 times 25 and tell me what we get? 5,775. Okay. So what this means, ladies and gentlemen, I couldn't do it because it wouldn't go that far. But I want to know what the pressure would have been if the sensor would have let me go down to 20 milliliters. So I can predict the new pressure at this new volume because it should equal 5,775. So now to get this number alone, I'm going to divide by 20 milliliters. What I do to one side of an equation, I'm going to do to the other. So could someone take that 5,775 divided by 20? Now, we could not find that with our sensor. Why? It was too high a number. The sensor just couldn't read that. But we can literally predict it now using this. Okay? We can predict it now using this. And the way people will do it, ladies and gentlemen, is they won't do what I did here. They won't set it equal to K and K. They will do this. 231 kPa times the 25 milliliters equals the new pressure times the volume we changed it to. They do P1 V1 equal to P2 V2. Instead of setting them equal to K and then using K in the second formula, they just set them equal to each other right away. Now, again, this side I'm going to divide by 20 milliliters, correct? To get P2 alone. What I do to one side, I do to the other. Somebody take 231 times 25 divided by 20. Tell me what you get. What do we get? Something isn't right there.
I got 288.75.
Are you sure you got the 231 and the 25 right? And then divided by the 20? And you didn't accidentally type something in?
I got 288.75. Ethan, what did you get?
He got that same thing. Kiana, I think you accidentally either switched some numbers around or something.
No, I'm getting it.
You get 288.75? Okay, sorry. I thought you gave me a different number. My bad. Okay? Point is, either way, we get the same number, and this is in kPa. Okay? Why? Because we're finding the pressure. And this is what Boyle's law lets us do, ladies and gentlemen. We could find something at a very low volume. We could find something at a high volume. Why? Because a constant is a number that does not change. That's how we get that straight line. And it doesn't matter if we look at one end of it or the other, we could find any new pressure, any new volume we wanted. And you could pick one. Maybe you want to know what the new volume would be if the pressure became 400. You could figure it out. Okay? You could figure it out. That is the advantage of Boyle's law, ladies and gentlemen. Now, we will not do this. No. That is something that we are not going to do. But I will ask you, what happened to the volume here?
It decreased.
So what's going to happen to the pressure? What? Yes, that I will ask you a lot of times. That I will ask you. That is the relationship. I will ask you about the relationship. I will not ask you to do the mathematics. So if the volume goes down, the pressure is going to have to go up. If the volume went up, pressure would go down. If pressure goes up, volume goes down. We can ask you either way. If pressure goes down, that's what I'm going to do with you on the test. That's what I'm going to ask you about. Not going to ask you to do this mathematics. But I am going to ask you to figure out what's happening to the pressure here or the volume here. Then what's going to happen to the other one. So I'm going to ask you about the relationships. I am not going to ask you to do the mathematics. Questions? All right. I do want to get through one other thing. By the way, on the next page here, ladies and gentlemen, there is a FET, which is an interactive that you can play with if you wish. You go to it and you can go to this, and it has all these different things, but you can do click ideal gas. Now, what this is going to allow you to do, ladies and gentlemen, is literally change any one of the 4 variables that we have been talking about. Right now, what's inside this container? Nothing. So how much pressure is there? 0. So the way you put gas in this container, ladies and gentlemen, you take this handle, you go up and down, and you just put a bunch of gas molecules in there. Okay? You just put a bunch of gas molecules in there. Now, what do you notice about the pressure? It rose. Why? Because particles are now doing what? And hitting the walls of their container. Okay? Here's our temperature. We haven't gotten to it yet, but if you wanted to heat it up or cool it down, you could. What would happen if I heat it up? They would move faster. What would happen if I cool it down? They would move slower. Over on the side, ladies and gentlemen, you can adjust the volume of the container. I made the container what?
Smaller.
What happened to our pressure?
It rose.
Went up. Why? Smaller space, the particles are hitting the walls more often. I could make it a larger space. Now, the volume increased, the pressure decreased. So you could change the temperature, the volume. You could change the amount of gas by doing the pump more, or you could change the amount of gas by opening the top, letting some escape. Okay? So, again, this is an interactive that can let you play with all 4 of the things that we have been talking about. And literally, like I said, you want to add heat, you go down to the bucket, you add heat, the temperature's going up. You add ice, the temperature goes down. Pressure is changing as well, right? You can play with all of these things in this one interactive. Okay? So it's something, hopefully this can help you visualize. It's not just me saying, imagine a ball hitting that wall and then hitting there and then hitting there and then hitting there. Here you can see the particles and how they move around. Here you can see the effects of adding heat or cooling it down. Okay? Here you could see the effects of changing the volume of the container like we did yesterday. Here you could see the effects of adding more gas. Matter of fact, down in the bottom here, if you wanted, you could even change the kind of gas particles that you're adding. We're adding heavy particles in here. You could take those out and add light particles if you wanted. See what the difference would be.
Can you do half and half? Half
Yeah, you can, yeah. It gets a little bit more confusing there, but you could do it. So if I take light, oh, here you go. So, what do you notice about the red ones compared to the blue ones? Why are the red ones faster? No, they're at the same temperature. What about the mass? Okay, so remember, to be at the same temperature, you have to have the same what? What is temperature? Kinetic energy. So a smaller particle to have the same kinetic energy as a heavier particle needs to move faster. You can actually see that in here. You can see that in here. Okay? By the way, the pressure went up when I added those other particles. Why? If I add more particles, the pressure goes up. Why? There are more things to hit against the wall. That's pressure. How often? It doesn't care what's hitting against the wall. It's how often something is hitting against the wall. So if I add more gas in there, the pressure is going to go up. The pressure is going to go up. Why? Because I left volume the same. If I make volume change, well, now pressure will change again. Okay? So again, it's just something you could play with if you wish to, ladies and gentlemen. All right, I got one more thing that I want to get through today, and then we will call it a day. And that is, we're going to quickly talk about the next gas law, which is called Charles' Law. And the reason we're going to talk about this is because you could see this law happen in Wisconsin. Charles was another scientist. He worked with two different variables. The variables he worked with, ladies and gentlemen, were volume and were temperature. He said the volume of a gas will vary directly to its Kelvin temperature at a constant pressure. Now, there's a key word in there before temperature, and it is what? Kelvin. We're going to show you tomorrow why you have to work gas laws in Kelvin, not in Celsius. Okay? And there is a reason for it, and we'll talk about that tomorrow. But now, instead of being in an inverse relationship, volume and temperature are in a direct relationship, meaning if one goes up, the other, no, not goes down, goes up. If one goes down, the other goes down. When have you seen this happen in Wisconsin, ladies and gentlemen? The volume of a gas goes down because of temperature. No. You actually see an object get smaller that is filled with gas because of the temperature. What? Okay, a ball if you go outside when it's cold. If you keep a soccer or a basketball in your car on a cold day, and then you go inside and you're like, yeah, I want to play some basketball at the Y. So you bring the ball inside, you hit it, you bounce it, and it don't bounce. Why? Because the temperature outside was cold, the gas inside there is taking up less space. Now, it's a little bit harder to see with a ball, but you can really see it if you buy somebody a Valentine's balloon. Because you buy them this nice big Valentine's heart in the store, you take it out to your car, normally in February in Wisconsin, it's cold. What happens to the balloon as you're walking to your car?
It slowly starts to deflate.
Starts to deflate. It's not actually deflating. Deflating means the gas is going out. What's happening is because of the cold weather, the volume of the gas is shrinking. So you walk back into the store and you're like, hey, you sold me a defective balloon. This one leaks. And while you were standing in line, the balloon goes right back to what it was before.
We had a lot of them on the
Yeah. It is not that the balloon is deflating. It is not that the balloon is losing air. It is that it is cold outside and the volume of the balloon has gone down. That's what Charles' law is. He said pressure and amount of gas are held constant. So, in Boyle's law, it was inverse. We multiplied the two, correct? Charles is direct. What are you going to do to the two variables if it is a direct relationship? Direct is the opposite of inverse, right? What's the opposite of multiplication? Division. V over T equals a constant. V1 over T1 equals V2 over T2. Okay? Short video here, ladies and gentlemen. Here we go.